Hi, guys. Welcome to another episode of Cuda Education. Today, what I want to do is follow up on the switching Q families discussion. Uh, the previous video directly before this one, I had my whiteboard and we were discussing switching Q families, and it's switching Q families, not switching family Qs. So it's Q families is the correct phrase. So this video, I wanted to actually show the algorithm. So remember, it's a compute cloth.cpp algorithm. So I'm just going to basically run it now and show you guys what it is. So as you can see, you have the Vulkan cloth, and it basically wraps around a sphere. And I could simulate wind, and as you can see, the wind now is affecting how the cloth moves. And I could turn back off the wind, and you see it kind of just lies back, stand still, right? And the sphere is underneath it. All right. So that's the script. That's the algorithm. And again, you guys want to run this on your computer, on your Windows-based computer with a GPU capable, a Vulkan capable GPU. Tutorial number 1 and tutorial number 13. Again, that's tutorial number 1 and tutorial number 13. It is. It will, tutorial number 1 is for you to install Vulkan on your Windows machine. And then tutorial number 13 is to install all these examples here, as you could see, all these examples, right? But we're just going to focus on compute cloth for now. All right. So the first thing I wanted to do was to remember, we're talking about switching Q families, right? And there were two Q families we discussed. We discussed the graphics Q family and the compute Q family. And we talked about how there's a difference, between graphics based stuff and computationally based stuff. So what I wanted to do was I wanted to kind of give a very rough example of what happens, or to just give an example of what I mean by there's graphics and then there's computation, right? So I'm going to rebuild the algorithm. I'm going to change the position of the sphere, but it's not what you think. I'm going to change the position of the sphere, but I'm changing it computationally. I'm not changing the graphics of position of the sphere, okay? So notice that this is all part of compute, right? So, well, at least this part, all right? This part is all part of compute, okay? So I updated the position of the sphere to be, so look what happens. Look what happens. The graphics of the sphere is here, right? That's where we visually see the sphere. But then the computation of the sphere is over here, right? So I just basically move the computation of, what the sphere is over here. And even though there's nothing here, it seems empty. Computational wise, that's where the sphere is, okay? So I don't know if that kind of helps you to appreciate the fact that there's graphics and then there's computation, but that is just my take on how you how you will see the difference between the two. Okay, so the next thing that we want to do is discuss the various functions that we talked about. So we talked about add graphics to compute barriers, right? And this is basically releasing things so that from switching from graphics to compute. And remember we said that it all boiled down to this discussion right here. Source queue family index and destination queue family index. Now, notice that the source is graphics, the destination is compute, and here, depending on where this is called, it would either be a release or an acquire. So if you call this while you're in the graphics, currently in the graphics family queue, if the situation or the ownership is currently on the graphics family queue, and you call this function, you're basically simulating a release, right? Because the current queue family and the source queue family is one and the same, right? However, if you run this and you're in the compute queue family, if your code is currently running in the compute queue family and you call this, this would be an acquire action, because your current queue family and your destination queue family matches, right? So as you can see, add graphics to compute barriers. So the source is graphics and you're going into compute, right? So you're moving from graphics to compute. You have add compute to compute barriers, which I don't really want to discuss now because I still need some time to fully digest it. But based on what I understand so far, when you have the source and the destination equal to each other, that basically means that you're relinquishing it from any queue family. But I need more time to really discuss that. So we have add compute to graphics barriers. So we have our source as compute and we have our destination as graphics. And in this situation, we're moving from compute and we're going to graphics barriers. I mean, we're moving from the compute queue family and we're going to the graphics queue family. And then that's pretty much it for the functions. You know, we have our source and our destination and the different queue families, and of course it depends. Now, one of the things that I will note is that this build command buffers, don't ask me exactly how this is performed exactly, but when this is running, you're in the graphics queue family, okay? So when build command buffers is running, you're in the graphics queue family. Now, when we go to build compute queue family, now you're in the compute, build compute command buffer, sorry. When you're in build compute command buffer, you're in the compute queue family. So why are these things important? Why am I mentioning this? The reason I'm mentioning it is because, for example, let's go back to build command buffers, which is graphics queue family, right? So if you're in graphics queue family and then you run add compute to graphics barriers, right? So add compute to graphics barriers. Let's investigate that. And we're in the graphics queue family. Okay, add compute to graphics barriers, right? So if you go up here, add compute to graphics barriers, you're going to see that you're currently in the graphics queue family. So that means that if your destination matches your current queue family, then that means you're in an acquire operation. So you're basically acquiring the storage buffers or the memory access or the access to, what it is that you're working on. This boils down to an acquire operation. Okay, so that's pretty much it. And this same thing run on in a different scenario. Let's say you run this in a scenario where you're in the compute queue family, then it would be considered a release, because the compute will match the source. So that would be a release operation, right? So let's get back to this. So here we have the build command buffers, which is graphics side stuff. So it makes sense that we have add compute to graphics barriers, because we're trying to acquire storage buffers from the compute queue. So we're switching from compute queue to graphics queue, right? So this makes sense here. We could logically understand that. Whole bunch of other stuff which we're not going to get into now. Now build compute command buffer. Now this is computational stuff. So you're building the command buffers for doing compute related activity, not graphics, but compute related activity. Okay. So when you're doing that now, naturally you would run add graphics to compute barriers, because you're switching from the graphics queue family over to the compute queue family. So you would naturally run this, okay? And again, if you're in the compute queue family here, where this is running, and you do add graphics to compute barriers, right? Let's look at that. Add graphics to compute barriers, and you're in the compute queue family, then you're going from graphics to compute, and your destination matches the destination matches the current queue family that you're running in. So this would boil down to the add graphics to compute barriers. This would naturally boil down to an acquire operation. So you're acquiring the storage buffers from the compute to the graphics, because again, the compute matches the you're currently in the compute queue family, and your destination DST is compute. So it matches the destination, so it's an acquire operation. There are a couple other nuances to this that I wanted to touch on. Notice that at the end of the build compute command buffer, right? This is, you're building the compute related command buffer. Notice at the end of it, after everything is processed, you release storage buffers back to the graphics queue. And notice now we run add compute to graphics barriers, okay? We run add compute to graphics barriers, but now the situation is a little bit different. In this situation, you're still in the compute queue family, right? So add compute to graphics barriers. So add compute to graphics barriers. Add compute to graphics barriers. So in this situation, you're currently in the compute queue family, and you're matching the source SRC. You're matching the source queue family of this mask, right? Of this function. You're matching the source. And remember what we said. If you're matching the source, if you look at the previous video, if your current queue family matches the source, then this boils down to a release operation. So notice how the author of the code says down here, he says, release the storage buffers back to the graphics queue. So when you run add compute graphics barriers, add compute to graphics barriers, this basically boils down to a release function, simply because of the fact of what you're doing it on and where you're doing it. You're doing it on a something that's in the compute queue family. So this boils down to a release action. Now, if we this function was also called under the graphics build command buffers. This is graphics related stuff, right? So notice that it was called here, but here your current state, your current thing that you're in is in the graphics queue family. So because you're in the graphics queue family here, right? Your current queue family matches the destination queue family. So this is an acquire operation. Again, if you're not sure what I'm talking about, watch the previous video. But you see, same function called, but different action. And that's all because you are running these things, you're doing these things with a different set of different environment, basically. So you're currently in compute here, and you're currently in graphics in the previous call. So one is a release, one is an acquire, but it all basically helps to transfer from, in this case, transfer from compute to graphics, right? That's pretty much it. Now, again, I said add compute to compute barriers. I'm still it basically, I'm not even too sure why on the last iteration you're releasing this and all that stuff, or you're not doing this. But my understanding is that this is saying that there's no ownership, like no Q family owns the storage buffer or what have you. But I still need time to really understand it. The issue basically with add compute to compute barriers, the issue with that is this, is that you have, unlike in the other functions, you have here where the source and the destination mask are equal, right? So what the documentation is saying is that when they're equal, it's like no Q family, no ownership, all that stuff. But that's where that is, and I'll just kind of walk through what this is saying. So we're currently in the compute queue family, and we're building the compute command buffer, right? And it's basically saying, if you're not in the second to last iteration, and notice that this condition is j is less than iterations. So if you're not in the second to last iteration, then you're going to run this thing, add compute to compute barriers. But if you are on the second to last one, which would be the last time this is run, then you would skip this. You would skip add compute to compute barriers, and then you would just run this down here. You would, release what have you. It might have something to do with the fact that, remember, this for loop only goes up to here. So I guess on the very last one, you're basically just gonna release it anyway. So what have you? But I'm not gonna get into that. I did also, this video is running a little bit too long, but I did also want to do something crazy. I wanted to comment out all of the switching code, right? I might miss one or two of them, but I wanted to comment out all of the switching code and see how it behaves. And of course, I wanted to do it for you guys so that you will also see the behavior. All right, save. And then let's build, and then I'm going to run it. Come on. All right. Okay. All right, so notice something, guys. Notice something. This is why it's important to always have code running on your machine, so you could tinker with stuff and see how it behaves. Now, one thing I notice is that, well, does it give you 9? Okay, so it gives you the frames per second. But from my observation, I will run it one more time, right? But from my observation, when you take out all of the Q family switching functions, it still runs, it still works. But if you ask me, well, I'll let you guys be the judge. So I'm going to undo all right, so I'm going to undo taking out all of the switching functions, and I'm going to run it again. All right. Now, if you ask me, it runs a lot faster. At least it seems to run a lot faster, or more smoothly when you have the sorry, when you have the switching functions on. Like the cloth seems to drop a lot faster, and the renderings and everything seems to happen a lot more smoothly. Right now, I don't know, this might tell you something different. So I'm just trying to make an observation here. So let's comment out everything again one more time, and see what happens. All right. So you notice, guys, how for whatever reason, and this is a little misleading, I guess, but um, I, I I don't know if because you're not switching or whatever, it just plows through it, but then the actual representations, doesn't match up. I don't know why this would show faster, but you could definitely see that as far as rendering is concerned, you're not getting you're not it's not running as smoothly in terms of the speed of the animation or rendering, right? It's not happening as fast. Okay, so there you have it, guys. Let's just do this one more time. So you see, it's a lot faster when you have the Q family switching done correctly. Um, and you could simulate wind and all that, and it does it a lot more smoothly. So that's my contribution to the world for today, guys. Remember, guys, I don't just want you to be watching the video. I want you to have Vulkan running on your Windows based machine with a Vulkan capable GPU. You can have this running on your machine too, and you could start messing around with all the code in here and making your different modifications and stuff. But Q family switching is important. You're gonna need to use this in other applications, working with Q families and all that stuff. So yeah, that's my contribution for today. Thank you for watching. Definitely check out the links below. I have tutorial number 1, link below, tutorial number 13. Remember, tutorial number 1 is to get Vulkan running on your Windows-based machine with a Vulkan-capable GPU. Tutorial number 13 is to get all of these examples here, all of these examples running. There's a previous video where I show you all of the examples. I'm not going to run through them again right now. There's even some ray tracing examples. So if you have a NVIDIA RTX GPU with that's ray tracing capable, you could run some of the ray tracing examples. So these ray tracing stuff right here. Okay. So yeah. I'll also have a link to the raw code on GitHub. But yeah, guys, I want you to follow me on this journey. I don't just want you to be watching the videos. You guys need to have it running on your machine, so that you could really learn Vulkan for yourself. There's no use in just looking at stuff if you're not gonna tinker with it and stuff. You mess with the command buffer, which is graphics related stuff, and then the compute related stuff. And then we saw earlier how this is the compute stuff, so you could change the position of where the computational sphere is, even though the graphics sphere is still in its original position. So that's another cool thing. And yeah, that's pretty much it. All right, guys, thank you for watching. Have a great day.